we have seen Charles' law and we have seen Boyle's law. Now let's see how these two laws lead to the ideal gas law. So that's the ideal gas law that I've written now in an earlier session. Now experimentally, as I've described, there is Boyle's law and Charles' law. And Boyle's law relates pressure to volume. It says that if you fix the temperature and apply more pressure to change the volume, then pressure times volume must always be the same number. Alright, this is with the temperature fixed. Now Charles' law says that if you fix the pressure with the pressure fixed, and say you increase the temperature, volume expands, then Charles' law says that volume divided by the temperature must always be a constant. And it's important at this point to note that the temperature must be in kelvins. Okay, now there's one thing about these two laws as well that I've mentioned before, which is that this constant, the constant number, it would be different for a different gas or for different mass of the gas, for example. Okay, so that's it. That's these two relations. Now, many years later, this ideal gas law was formulated. Now, what I like to show here is how this ideal gas law is related to Boyle's and Charles' law. Right? It is actually derived from these two laws, as well as some other information that I'll talk about. So let's start. All right, let's see how this law is related to Boyle's law. So starting from this idea that the temperature is fixed, let's have a look at the ideal gas law. If the temperature is fixed, then the ideal gas law, I'll write it down here again. P, pressure times volume, is equal to nRT. Now if the T is fixed, that means this is fixed. Okay, and we know that R is a fixed number, and N is the number of moles, which is related to the number of particles in gas, and that's fixed as well for the same box of gas. So that means that as long as T, the temperature, is fixed, all these three numbers to the right of this equation are fixed. In other words, these three numbers is, the product has to be a constant. Constant in the sense that it's a number that doesn't change if you change the pressure or volume. Okay, so we must always be careful about what we mean by constant. It doesn't mean that it's constant in any situation. Just in this situation where we fix temperature, and it doesn't change if we change the pressure and volume. Now, so we see that when temperature is fixed, the ideal gas law has this behavior that it tells us that the pressure times volume is fixed, which is exactly the same as Boyle's law. So, in other words, by fixing the temperature, the ideal gas law gives Boyle's law. So here is one connection. Boyle's law. Let's have a look at Charles' law. Now, Charles' law is when pressure is fixed. Okay, so let's see. Pressure fixed. If pressure is fixed, let's see. Now Charles' law is about V over T. So let me rearrange this. I'm going to keep V here. Keep V here. Now I want to move T over here. So T comes down here. I want to divide both sides by P. So P comes over here. So the ideal gas law can be rearranged. That's P. That's T. Okay. So here we are. And this time is P that's fixed. If you now look at this new arrangement, we have P down here that's fixed, N and R are fixed. So therefore, the right hand side here is a constant. And the left hand side is V over T, which is the same as what we have in Charles' law. So therefore, we have Charles' law now that V over T is a constant. Okay. So this means that when we fix P, the ideal gas law here or here leads to Charles' law. So this shows the relation between Charles' law and the ideal gas. So ideal gas is consistent with both of these laws. Now, but the ideal gas contains some more information. It contains this N here. I'll talk about that later. And the R here. So if you look at this N and the R, look at this N and the R, it basically provides a complete equation that describes any gas. So unlike the constants in Boyle's law and Charles' law that can be different for different gases and different masses, and you just have to go and measure that, make the measurement for each gas and find out that constant. It's very it's lots of work, very inconvenient. But for the ideal gas law, the constants in the ideal gas laws are it's just the R. It's just R, and we already know what R is. R is 8.31 joules per Kelvin per mole. So it's a fixed number. It doesn't change if I change to another gas. Right? If I change to another gas, I might have a different pressure, different volume, different number of moles, different temperature. Doesn't matter. But the R would be the same. So that makes the ideal gas law a lot more convenient and a lot easier to use, and in a way a lot more useful.